Now a quite long video will follow, but it's an important argument and it's a bit difficult argument, so we need to spend some time on it, and I hope it'll be worth it. Okay, so first we need to remember that time can be measured in different ways. We've looked at this previously. You can have coordinate time, that people have different coordinate times, but you can also have proper time, which is something that is a way of measuring time that everyone can agree on. And so it's important to remember then that even if we have different coordinate systems for how different people move related or relative to each other, they can also calculate their own time and other people's time and agree on what time it is. So we saw the twin paradox. When Steve was sitting home, he would say that now the twin has been traveling for 5 years in Steve's coordinate system, but only 3 years in Rocky's coordinate systems. But Steve could also have calculated that he had been traveling for 3 years in his own coordinate system. And if they wanted to, they could have measured the same time. Steve could also have measured the same time as Rocky could have measured the same time as Steve. They could do this GPS adjustment that we are used to. We can fix clocks and make everyone measure the same time. That's no problem. So there are different ways of measuring time, and but we can agree on them and use the different ways without any discussion or problem. There are different advantages then of measuring time in different ways, and physicists doing relativity physics, they choose to measure proper time, because then they don't need to care about which coordinate system you are using, and since they are all equal, that seems like a nice way of doing it. It's also good that this proper time is actually linked to our biological aging, etc. So it makes good sense to use proper time. But we'll look at some disadvantages soon. One other thing to be aware of is that, in principle, all observers could also agree on the order of events, of how things happen in the universe. And I'll try to explain that with a figure. So here we have a coordinate system with time on the y-axis or the vertical axis, and space on the horizontal axis. And the green light is the green line is light. So if you go above the horizontal line, that's future, and below it's past. So it's imagine we're standing in the middle and emitting light, and to the right, you'll see that in one year, light will travel 1 light year. In 2 years, it will travel 2 light years, both to the left and right. But it's also, this is light below the horizontal line is light coming from the past. So light that was 1 light year away 1 year ago will reach us today. 2 light years away 2 years ago will reach us today, etc. And this figure is called the light cone. It describes how light spreads from one moment and how light can have reached one point at one moment. And what happens inside the light cone is something that all observers can agree on. The order of events. If it's far away from each other, outside of the light cone, then they will disagree on what happens first, what happens simultaneously, etc. But within the light cone, they can agree on the order of events. And that's why I said also that in principle you could agree on all the events in the universe, because we can imagine then this past light cone of the whole universe. And so if we could communicate across the universe, etc., we could in principle agree on the order of events. Now, if you use different coordinate systems, then you can decide that something is future or past or happens simultaneously in different ways. So if you look at this figure for the traveling twin, we see that stationary Steve, he has these vertical simultaneity lines. No, I mean horizontal simultaneity lines. Whereas Rocky, who is traveling, he gets a tilted simultaneity line, and the faster he will travel, the more tilted it will be like this, and then when he starts going home, it suddenly tilts the other way. That's the red lines moving, and then he will measure something else happening simultaneously with Steve. And now we can imagine that this figure, if we say that the middle point is when the Big Bang happened 13.8 billion years ago, we can imagine this green light as a photon, a light particle moving away from the Big Bang, and it will go 1 light year in 1 year, etc. And so after 13.8 billion years, it will still say that the Big Bang is simultaneous with what happens now. So you just say the Big Bang happens now. So the Big Bang has been now for 13.8 billion years for this photon in our reference frame. But if the photon suddenly changes direction and starts moving back towards the center, its simultaneity line will tilt like this. So it would say that all of the universe history was future. But suddenly it would then turn into past, and it would even be 13.8 plus 13.8 billion years would be now 27.6 years of billion years of history now for this. So it would suddenly, everything that was past will suddenly be, everything that was future will suddenly become past for this photon. So what it shows is that you can use different coordinate systems to categorize something as past or as future. But that still leaves us this question: can we say something more objectively than about what is future and what is past? And actually, we can define a global simultaneity for the whole universe. Physicists do that when they discuss how old the universe is. They don't say, if we ask a physicist how old is the universe, they don't say, well, for a photon, it's 1 second old. What they do instead is that they define a reference frame for the whole universe, and that's the reference frame where the background radiation from the Big Bang is similar in all directions. So it's correct that all reference frames are equally good just when you look at the reference frame as a reference frame, but the content of the reference frame can make some reference frames stand out as special. And in this case, the whole universe has one reference frame which stands out as special because of the content, the radiation from the Big Bang being similar in all directions. And that's the one that physicists use to say that the universe is 13.8 billion years old. Now that seems to, okay, then it seems to be an objective answer to what happens now and what is future and what is past, etc. But the physicists will still say, no, this isn't actual simultaneity defining a now. It's just this average that we make for the whole universe, but it doesn't work locally because we have general relativity saying that time is different depending on how much mass is present. So if you start looking locally, then the simultaneity line will disappear. So we can just say something general about the universe as a whole. We can't say this is the correct answer to what happens simultaneously or what is now. But even if the physicists don't want to, and they use a theory where there's no global simultaneity, philosophers can define the concept of global simultaneity, which we can do at least in principle then, even if we cannot do it in practice. And the way to do this in principle I can explain with a thought experiment. We can say that let's take this reference frame for the whole universe, and we imagine that there are cameras all over in the reference frame, and they're all synchronized. And so we take a picture, and then it will take a picture over the whole universe. And of course, some places there would be a black hole, and so it wouldn't be practically possible. But we can imagine this in principle, taking a picture of the whole universe, putting all the pictures together to have a picture of this is what happened at the same time in the universe. And that would then show us that some things were contracted, etc. But it would be what happened now in the whole universe. And so it would be a way to define global simultaneity. So now we need to make a discussion. Okay, so there's this one way of using proper time, using the theory of relativity to define time. But should we then say that what they say when they use their theory, etc., that applies and has consequences for how we understand the whole universe? Or should we think that when we have an understanding of the whole universe, etc., we need to think differently and use different concepts? Let's look at some arguments for and against using different ways then of measuring time. If you say that, well, we should just follow the physicists and say that there is no global simultaneity, and take the implication then that there's a block universe, well, that would mean that there are extremely many different universes in this block universe, all existing then in parallel. So there's the universe where I sit like this, and one universe where I sit like this. If you're a presentist, you would just say there's one universe, and it's the universe now is where I'm having my hands like this, and then the universe now is where I'm having my hands like this. But the block universe or the eternalist will say, well, there's this universe and there's that universe, and they both exist, and then you can understand that there are extremely, extremely many universes, because everything that happens has its own universe. And that means also that, well, what is time, what is a dimension or a different universe, we don't know. Even what are things, because things must then be connected. Instead of me, after being one person, changing around like this, there is a slice of me where my hands are like this, a slice of me where my hands are like this, and they're all connected. So it's like this big salami sausage of connected time slices of me and of all objects. So all objects and dimensions and time, everything becomes something mysterious and unknown that we can't observe, but that we hypothesize to be true. And then we can ask, well, how did this gigantic block universe come about? It's very strange that there should be such a universe. If either if you think that there's a God who created it, but also if you think that there's no God, it seems much more likely that there was this one universe changing, as we describe in cosmology and in evolution, etc., instead of there being this gigantic block universe where everything exists in parallel. And so evolution also seems to make much more sense. If in fact things can evolve either this or that way, and what is best, most evolutionary fit, etc., is what determines what happens. It's very strange. Why should it matter that my offspring are better fit for survival if just everything has always existed in the same way anyway? There is no difference. What would it mean to be better fit for survival if everything is just this frozen gigantic block universe and all motion is just an illusion? So these are different arguments against eternalism that should make us favor presentism instead. But you can also have some arguments for eternalism. For instance, you could say, well, physics has taught us that we live in this four-dimensional space, so we'll just have to accept it even if it's strange. But that's not true. It's also possible to think that, well, four-dimensional space, that's a geometry that we use to describe the universe. But what actually happens, that happens because of the laws describing how things should move, how things should contract, etc. But there's just this one present universe, and it's useful to describe it with relativity physics. So some who argue like that is, for instance, Harvey Brown or Michael Asfeld. Other people have said that you don't have to dismiss relativity physics, but you can apply it to this presentist universe. Because in fact, relativity geometry is full of possibilities that everyone agrees is impossible. So it's a big theory where you have to say these are things that actually describe the physical reality, and these are elements that we must just throw away. And that's something we must discuss. What should we believe is true? And I'm arguing here then that we can say that there are these actual movements, and some motions happen slower, some things contract, etc. And that's good to describe with this four-dimensional geometry. You will probably see good physicists, etc., saying that no, there is no real contraction and slowing down, etc. It's just how we describe something relative to a reference frame. And so Tim Maudlin, he quotes how John Bell, he made a big survey at CERN, so some of the best physicists in the world, gave them a thought experiment, which showed that they all thought, no, It's just it's no real contraction and real slowing down of motion, etc. But that's wrong. There is you can read more about that in Molden's book, and we did see also some experiments showing how iron atoms they slow down, etc. So it's a real effect in the universe that happens. Another argument is that you could say, well, space seems to be a thing that can expand because the universe is expanding. The space of the universe seems to expand because it's 13.8 billion years since the Big Bang, but the radius of the observable universe isn't 13.8 billion light years, it's 46.5 billion light years. So space itself seemed to have expanded, as something you will also often read. Space itself expands. But that's just a way of saying that these objects in space, they are moving apart from each other, like buttons on a balloon, etc. And they can do that without breaking any. That seems to contradict the speed of light, but that's something that you can't move faster than the speed of light within one reference range, but you can't define this so-called inertial reference frame for the whole universe. So there is no laws of physics are broken, even if the universe is bigger than 13.8 billion years in its radius. So, to sum up so far, you can use different coordinate systems to define something as future and past, as we saw with the photon, etc. But it doesn't follow then that, okay, now we have this objective past which has been settled, and that we should say that the future has also been settled. Physicists, they have their way of measuring time. They will reject global simultaneity as they define it, but we can define it in another way, and it makes sense, and it doesn't exclude. You can do this philosophically and say this about the universe, while also saying yes to all of the relativity physics. So that's what I'm arguing, that we should say okay to relativity physics, but not that it not take the implications that it seemed to have. If you just say that this sense of the terms is what should apply to the whole universe, we can say that there are other ways of understanding the terms that makes better sense and gives us a more plausible worldview. And so it's possible to say, well, what's taken at this picture is the whole universe. That's all that exists. Physicists, what they say and do is right if we understand it the way they define it, and we don't have to define it in the same way, but we can keep physics and we can keep a presentist understanding of the universe. And that will have all the advantages that we saw now with the different arguments against eternalism. But there are also many other arguments for and against eternalism and presentism, and we'll look further into those in following videos.